Hello, I'm Luke Gibson, a fifth-year PhD candidate in Jim Fentner's group at the University of Washington in Seattle. Today, I'm excited to talk about a project that I worked on during my time at the Pacific Northwest National Lab under the guidance of Dr. Chris Mundy. Now, as the title of my talk suggests, I'll be talking about how we're constructing a workflow for computing electron transfer rates within a heterogeneous system where we have a model graphite anode reducing liquid electrolyte. And I'll briefly cover Marcus theory and the main quantities that are involved, as well as how we use molecular simulations to compute these parameters. Now, nobody needs to be convinced of the importance of batteries today. They have many applications ranging from small handheld devices to electric vehicles, even up to grid-scale storage. However, these batteries are not without their drawbacks. The most popular battery chemistry is the lithium-ion battery. And these batteries are extremely powerful due to their large power densities. And here we have a schematic of one with many of the modes of capacity fade shown. And I like this figure because it gives you an idea of the complexity of the processes occurring within a battery. Now, the common components of the battery are listed here with example materials. First, we have the anode. On the other end, we have the cathode. Between them, we have the electrolyte, which contains your lithium salt and your electrolyte solvent, which helps shuttle the ions back and forth between the electrodes. We also have this solid electrolyte interface layer, SEI layer. I'll be coming back to this. And last, we have the separator, which helps prevent any electrical contact between the electrodes. Now, any of these mechanisms that are shown in this diagram can be the topic of a full PhD. However, I'm focusing on number 4, the solid electrolyte interface, or SEI, which is a layer that builds up on the interface of the anode and at the interface of the anode and liquid electrolyte as a result of electrolyte degradation. Now, we're doing this because the formation of this SEI layer is known to be one of the main causes of capacity fade. However, it's still not well understood how it grows. Now, if we zoom into the atomistic level where we have the electrode surface, we can see several processes that are occurring during charging, which are listed here on the right. Here, we have a graphite anode surface in contact with liquid electrolyte, which is ethylene carbonate. Now, only one is shown here for clarity. However, we do have the full liquid phase of ethylene carbonate directly contacting this interface. So first, we could just have lithium intercalation, which is the preferred process during charging. However, we could also have an electron hop from the surface onto one of the electrolyte solvent molecules. Now, if the temperatures are low enough and the voltage is high enough, we can even have lithium plating, where a lithium ion is reduced to lithium metal and deposits on the anode. And there's several other processes that can also occur. So this now brings us to the goal of our study. Firstly, we want to construct a workflow that allows us to compute the rates of electron transfer. And a good starting point is to use Marcus theory for that, which lets us use this equation here at the bottom to estimate the rate constant for electron transfer, given a series of parameters. And secondly, we want to ultimately better understand this first step of SEI growth, where this electrolyte is reduced. And in our study, we'll be looking at 3 acceptors to get a qualitative picture. First is ethylene carbonate. The second is just a lithium ion. And the third is a combination of the two, where we are looking at an ethylene carbonate that is in the solvation shell of a lithium ion becoming reduced. But before I get too far, I want to briefly explain Marcus theory for anyone who's unfamiliar. So in Marcus theory, we ultimately construct 2 parabolas that portray the free energy profile along some reaction coordinate on the x-axis, which we'll see is largely a solvent orientation coordinate. Now, if you have these parabolas fully defined, you can ultimately compute your rate of electron transfer. But there's a lot of nuance to these parabolas, and I'll go through how their shape and locations affect the calculation. First, we have the gray curve on the left, which denotes the reactant state, which is depicted here on the left. And in this state, we have the charge localized on the donor species, and we see that the solvent orients appropriately due to this localization around both the donor and acceptor. On the other side, we see the gold curve, the product state, where in the basin, we have the charge now localized on the acceptor and the solvent has reoriented in response. Now you can imagine that if you have a reactant state and just freeze all atomic coordinates, but transfer over the charge, which would look like this vertical excitation, we would be hopping over to the product curve, but the same reaction coordinate, which would yield a much larger energy, which is shown here, where the solvent coordinates are the same, but the charge is now transferred over to the acceptor. So this helps us orient ourselves when looking at these curves and helps us understand what each point represents. So going back to Marcus's equation, we see that there's three parameters that we need to compute in order to calculate the rate. And each of these quantities are depicted in the plot on the right. First, there's the electronic coupling, VAB, which is a quantum mechanical parameter that describes the overlap between the reactant and product states. An important aspect to understand is that if this coupling is large enough, these curves reform to produce two adiabatic states, where the gray curve is your ground state, and this gold curve is your excited state. Now, the second term is the reorganization energy, which is quite literally the energy of relaxation after we freeze the atoms in the reactant basin and transfer the charge via that vertical excitation. And then from that point, we let the system relax, and that gives us our reorganization energy. And so this quantity is actually governed by purely the horizontal distance between the two parabolas, as well as the shape of the parabolas. Now, lastly, we have the free energy of reaction, which is pretty straightforward to see on here on the plot. It's just the vertical offset between the two parabolas. Now that you're up to speed with the major aspects of Marcus theory, I'll quickly cover a study from Elon Benjamin's group that inspired a lot of our work. Now, in this study, Rose and Benjamin looked at electron transfer from an electrode to an iron 3 ion in water. And the waters are just denoted here by the gray arrows. Now, on the left, we see the Marcus parabolas that they constructed, where the x-axis is just the electric potential on the acceptor species, or the iron ion. And you see here this U0 term is just a constant shift that forces the crossing point of these parabolas to occur at 0. Now, this iron ion is strongly coordinated with 6 waters, which are denoted by these lighter gray arrows. However, once we transfer the electron, we see this change in solvent structure. It's subtle, but you do see a loosening of the solvation shell when you go from iron 3 to iron 2, since this iron is becoming less negative. But it's still strongly hexacoordinated. So this shows us that even small, subtle changes in the solvation environment can lead to large changes in the energetics. And we kind of follow a similar workflow in our work when we're dealing with ethylene carbonate reduction. So we see that these three parameters need to be calculated in order to compute our rate. And I'll go over how we plan on computing each of these parameters. I'll first start with the electronic coupling. And as I described earlier, this coupling parameter is quantum mechanical value that describes the overlap you have between the orbitals from your donor and acceptor species. Now, there's not enough time to fully describe the process, but we plan on using the projector operator-based diabatization process or method to compute these couplings, which simply just lets us define donor and acceptor regions in our system and compute the couplings between them. We then also plan to evaluate the configurational dependence of this coupling for each of the acceptors in our system. So we're going to look at distance from the surface as well as the orientation when at the interface. And the next parameter is the reorganization energy. Now, on the right, we have the Marcus parabolas that we constructed for ethylene carbonate at our electrode interface, with the x-axis being the same reaction coordinate that was used in Elon Benjamin's work that I described earlier, which is just the electric potential on the atoms in the ethylene carbonate. So to construct this curve, we couldn't simply just sample configurations in each parabola, because we'd only explore the area immediately near each minima, so just right around here. And so to produce the full curve, we employed an enhanced sampling technique known as umbrella sampling, which lets us run simulations in multiple regions along the x-axis and back calculate the true curve. And we actually did that here by changing the ethylene carbonate net charge from 0 to 1 in quarter charge increments. And so this plot tells us that the reorganization energy for ethylene carbonate here is approximately 38 kcal per mole, which is quite sizable and can't be ignored. And so lastly, we have the free energy of reaction, which is a much more involved quantity to compute. We see in equation 1 that this free energy is comprised of two other energies. The first is the free energy of solvation right here. And the second is the change in intrinsic energy as the charge is being transferred. Now this intrinsic energy is defined below in equation 2, where we have this delta E naught term right here, which is ultimately describes your difference in electronic states or in electronic energy levels. So that includes your electron affinity of your acceptor and your ionization potential of your donor. But we also see here this overpotential term, which has an external bias that raises your Fermi level, which will ultimately affect your free energy of reaction. And now this third equation describes your change in solvation free energy. Now there's not enough time to go into full detail about how this is calculated, but I'd be happy to explain it more during the live Q&A session. But its result is shown here on the right. We have the solvation free energy on the y-axis and the species charge on the x-axis. Now, as I said earlier, we're looking at 3 acceptors, each of which is shown on the plot. However, by the nature of the calculation, we computed the charging of a lithium atom to a lithium ion, which is actually the reverse reaction of what we're interested in this blue curve. And so the blue number shown here will actually be inverted to give a change in solvation free energy of positive 106.7 kcal per mole in order to reduce a lithium ion, while the other 2 quantities here are still negative. And so the overall trend we see is shown here at the bottom. A solvation shell ethylene carbonate has the most negative change in solvation free energy, whereas the lithium ion, as I just mentioned, lithium ion reduction is very largely positive. And so this, in conjunction with the intrinsic energy changes, suggests that ethylene carbonate that's in the solvation shell is likely to be the most favorable. So now, after a few assumptions, we can preliminarily compute rates of electron transfer and look at the trends of the three systems. Now, on the right, the y-axis, we have a plot where the y-axis is the natural log of the computed rate constant, and the overpotential that I mentioned earlier is along the x-axis. I should note that this overpotential is not yet aligned to a particular reference electrode, however. So given this, and that these are some preliminary results, the exact quantities are less important, and I want to focus more on the trends between the systems. And so in this, we see that for a range of overpotentials, the solvation shell ethylene carbonate has a significantly faster rate of electron transfer. However, after a certain voltage, we see that the liquid, just pure liquid ethylene carbonate, overtakes the solvation shell ethylene carbonate. And this is due to the presence of this inverted region, where an increase in the driving force or free energy of reaction will counterintuitively decrease the rate of electron transfer. And so, probably wondering where the lithium is. The lithium ion is not even shown here on this plot because it has an extremely small rate constant, which qualitatively makes sense. It would completely distort the axes on this plot. Now, it's important to note that while these models do have a lot of simplifications and are ideal scenarios, it's an important first step towards addressing a notoriously difficult problem in computing these rates of electron transfer in these electrochemical systems. And so the next steps of this work is to finish computing electronic couplings and reorganization energies, and then ultimately construct also a generalized Langevin equation to better estimate these rates, since we could then account for the explicit solvent fluctuations, particularly in the transition state region. And so finally, I'd like to thank my research group and of course my PI, Jim Fentner, I would also like to thank Chris Mundy and Sam Johnson for their helpful guidance and discussions throughout my time over at PNNL, as well as as well as all of my funding sources and computing resources at UW and PNNL. And so that's the end of my talk. So thank you for listening. I'll be happy to answer any questions during the live Q&A session on Thursday morning at 8 a.m. Pacific Standard Time. Thank you.